Multiplicative functions are examples of arithmetic functions. Arithmetic functions meet the following criteria. Their domain is the set of positive integers. Their range is the set of all complex numbers. Arithmetic functions map positive integers to complex numbers. Multiplicative functions are a subset of arithmetic functions such that the following criteria also holds true. An input of 1 will yield an output of 1, and an input of x, such that x is the product of primes, we'll call them a and b here, will yield a value equal to the product of the function's value taken at each of the prime factors of x. This means that to evaluate a multiplicative function at a given number n, we only need to take the value of the function at the prime factors of n, shown here as the product of prime powers p1, p2, all the way to pn. This property can be seen in arithmetic functions such as the Euler-Phi function, which determines the number of integers less than the input n that are coprime to n, the function which determines the number of divisors less than or equal to n, and the sum of the divisors less than or equal to n. Another example is the Mobius function. It assigns a value of 0, 1, or -1 to a number n depending on the prime factorization of n as shown. All of these examples can be understood by determining their values on the powers of the primes which divide an input n. Let's examine the Euler-Phi function in more detail. We'll compute the phi of n for some values of n in a table. If n is a prime number p, shown in red, we see that phi of p is equal to p minus 1. If n is a power of a prime, we can calculate phi of p to the k. To calculate phi of p to the k, we count the integers relatively prime to p to the k as those that are not multiples of p to the k. The multiples of p to the k that are less than p to the k are p, 2p, 3p, all the way up to p. Now there are p to the k minus 1, many of these. So what we want to do is subtract them all from p to the k. Then we get a formula. Phi of p to the k is equal to p to the k minus p to the k minus 1. We can understand multiplicative functions by using Euler's function as an example, where we write our input value n as the product of powers of primes. Then Euler's function at n is equal to the product of the values of Euler's function taken at each prime factor of n. This gives us a formula for phi of n, since we saw that phi of p to the k equals p to the k minus p to the k minus 1. By applying this formula to each prime power, we have the following statement. This is a direct result of its multiplicative property. We can evaluate phi of n by using this formula on the prime factors of n. All multiplicative functions can be evaluated using this prime factorization of the input.